Eye tracking is attractive for interaction as we naturally look at objects that we are interested in. However, eye tracking can easily become noisy and for some completely unusable, making interaction difficult. In this work, we address this problem via weighted pointer techniques for area-aware pointing based on fallback modalities. First, eye tracking accuracy, precision, and data loss is detected through an eye tracking calibration. Second, a modality weighting model utilizes the error data to decide on the weightings between gaze and the fallback modality. Finally, the weighted pointer technique uses the weightings and the modalities to calculate and display the pointing direction. With these components, we can adapt the interaction to the eye tracking error. Here we have the same example, but with our techniques in use. When the eye tracking is stable, the interaction relies on gaze pointing. The interaction, visualized by the cursor, will rely more on the fallback, in this case head pointing, when gaze deteriorates. The weighting between gaze and fallback is visualized via cursor transparency, and the interaction will fully rely on the fallback modality when the gaze signal is deemed unusable for interaction. We explore 4 different techniques to use as fallback for the weighted pointer. The hands-free weighted pointer uses head pointing as the fallback modality to allow fully hands-free interaction. As the head is a natural part of our gaze, the transition from gaze to head is simple as the pointer is always within the field of view. The controller-based weighted pointer uses controller pointing as the fallback modality. The pointing origin is always set to the gaze origin, i.e. head tracking, to avoid confusion during modality transitions. Therefore, the technique only requires a 3 degree of freedom controller for interaction. The relative technique uses relative hand movements to minimize the required hand movement and allows adjustments from a lazy resting position. The controller movements are made relative to a calibrated neutral controller direction, and the rotational offset between is applied to the gaze direction as the fallback modality. The trimodal technique uses relative controller movements like the relative technique, however the rotational offset is applied to the head direction as the fallback modality. This allows for a combination of head and controller movements to be used to adjust the pointer direction. Large adjustments can be performed with less straining movements because the refinement is distributed to both modalities. In contrast to the relative weighted pointer, the fallback modality is not based on the gaze direction and is thus more stable during high levels of precision error and data loss. The techniques were evaluated in a VR user study against a manual baseline at different eye tracking error levels. We found that participants were equal or significantly more performant compared to the baseline techniques, and that our techniques were preferred by a participant majority. Please refer to the paper for full study details and results.